This talk is composed of two parts. So the general theme is about scaling blockchains, and the first part would be about how to increase throughput to achieve an arbitrary throughput, actually. And the second part would be to achieve sub-second latencies. So I'll first give a very short introductions about what blockchains are, and only enough to know what would be needed to the rest of the talk, basically. So no. Yeah, I cannot move the slides. Right. Okay, so that's the setting we're working on. We have a set of nodes. So the green nodes are the honest nodes. And then we have some bad nodes, the red one with a cross on top of it. And we always keep the assumption that we have more than 2/3 honest nodes. So here's how it works. So we have a client in yellow on the left that builds a transaction. It builds it locally. That's step one. Then it submits the transaction to the network, which is seen as a whole system. The system processes the transactions, sequences it, verifies it, and then add it to storage. In our case, it will add it to a blockchain. So how would it work? The killer example is always the same. Imagine that Bob wants to send 5 coins. So he builds the transaction saying, I want to send 5 coins to someone else. He signs it, send it to the system. As a whole, the system would see if the payment is authorized in multiple ways. So is the signature valid? Is there enough funds for Bob to transfer? And if everything is fine, eventually it will add it to the store and so add it to the blockchain. So traditional systems like Bitcoin suffer from high latency, slow finality, and slow throughputs. So those are 3 inconveniences that usually we will try to solve all or at least some of them through all the modern systems that we're going to see. So what does it mean? So high latency. So this simply means that it takes a long time in order to see the transaction committed. So before, it takes a long time between sending the transaction and the time it's indeed arrived to the store. Slow finality means that, sure, once it's there, it might even be reverted. So we might need to wait even a little longer just to make sure that the transaction would not be reverted, or at least with high probability the transaction will stay there. And low throughput, well, that simply means that the system cannot process a lot of transactions per second. So this is the outline of the talk. As I mentioned, we have 2 parts. The first is how to increase throughputs, and the second one is to reduce latency. There are many ways of achieving both goals, but here we'll just focus on some. So for increasing throughput, we'll go through the sharding techniques, and to reduce latency, we will do it through the mean of a side infrastructure. So this is a bit of an outline for part 1. So this is just for you to keep the slides, and the same for part 2. The main takeaway that I would like you to have is at the end of part 1 to get the key concepts of how sharded distributed ledger works, and also the main challenges in building them in practice. Because as you will see, there was a long road between the moment where we were able to build on paper and the time that we made them work. Then the second part, I would just like you to remember how a side infrastructure can be used to bring blockchain-based payments to physical point of sale. So the latency should be extremely low, and how to integrate those side infrastructure into a main blockchain, of course, so that we don't have 2 separate systems at the end. So what is not covered, so in order to have a fully workable system, there are a bunch of things, right, that are absolutely not included in this talk. The first is the privacy on blockchain, because a priori everybody can observe the blockchain and potentially learn about transactions. The second one is the Sybil resistant mechanism, the way we select nodes to participate in the blockchain. traditional techniques are proof of work or proof of stake. Those are not part of the talk. And the last one is the incentive of node operators. Then, of course, there are other things like governance, which are also not included here. Okay, so this is part one, increasing throughput with sharded blockchain. So as we mentioned, this is the traditional system that we see here. We have clients and we have a global system with some nodes good, some nodes bad, right? And usually there are three main techniques to scale blockchains. There are other, but those are the biggest that we have. The first on the left is to use some kind of side chain in order to have more throughput, some through the main chain and others through the side chain. The middle one is sharding. And the last one is a different technique where you would simply sample a fixed number of participants and then just run consensus among those in order to sequence the block and execute the transactions. And this talk would just about be sharding. So what we hope to achieve here, we hope to have a high throughput, BFT resilience, fast finality, and some linear scalability. So linear scalability is something which is proper to sharding techniques. The idea is that the more machine we have, so the more hardware we invest into our system, the bigger the throughputs. So this is how we define scalability for the scope of this talk. So here is how it works. So we have the usual system, and when we groups of nodes, shards, among all of from the total nodes on the systems. We make sure through random sampling of various techniques that the bad node, so the red one, are fairly equally distributed among all the shards. We don't want one shard having all the bad nodes and another one having all the good nodes. So what will happen then is that instead of running the global consensus among all the nodes, we would run consensus within each shard and then run a special algorithm called the cross-shard consensus protocol across the shards. So this will have one main difference with respect to traditional systems. So usually you would have one global store, and here in sharded system, we would have each shard maintaining its own block. So particularly, we do state sharding, which means that every shard will be responsible of a subset of the state of the system, a subset of the objects. So for instance, here we see that one shard is responsible for object 1 and object 3, and would build a blockchain based on all the object it manages, but absolutely not about those that it does not. And shard 2 on the right would have object 4 and object 8, and other shard may be responsible of other objects. So this is just a recap. That would be the main difference. Instead of running global consensus algorithm across all nodes and building one big blockchain, sharding technique would say, well, we'll have a smaller group called shards, and each shard will build its own blockchain, separating the states across all those shards. So this is how it would work. So let's look at the transaction, the one on the slide, and I'll use the same notation across all the section 1. So X1 is an object living on shard 1. X2 is an input object living on shard 2. What we would like as the outcome of such a transaction is that once it's executed, X1 and X2 are consumed, so their object does not exist anymore, but output 1, Y1, output 2, Y2, and output 3, Y3 are created instead. So this should happen. So now it's important to note that there are only two possible states, valid states for the system. Either the one on the left, where all the input objects are there, this means the transaction failed, but cleanly failed. And on the right, where the transaction succeeds, so we don't have the input object anymore, we only have the output object. Any other state where we have a mix of input and a mixed input is not a valid state and is considered a safety violation. So now that's the question of how sharding works. We will just focus here on how to build those links across the shards. And I will use some of the techniques that are described in multiple papers like S-BAC and Atomix that would explain how those works based on techniques that are a mix of Byzantine agreements and a two-phase atomic commit, in case you've heard about those. There are other techniques, but those are two of the main techniques used out there. So just a spoiler alert, I will explain you how they work, and then we'll see that even they would work in theory, they're insecure under parallel compositions, that there will be some attacks against those. I will show you how to go through, and then how to fix them. They could be quite subtle, so they were not easy to spot at all at the beginning.
Alberto, can I interrupt you for a little bit? Unfortunately, we have some technical difficulties since your video is kind of freezing. Can you turn off the video for a little bit? Like, and we will. Can you turn off the video in your vMix thing? And probably we'll. Yeah. Okay, I thought that I will talk with Grigory, but unfortunately, Grigory turned off. Okay, so, okay, Grigory, how do you find that? Great. How do you find the talk yet? I understand that nothing have happened, but like, what do you think? Is the sharding is a good idea to use, or you prefer other two options that are not that were proposed but not discussed? What is your opinion?
Well, definitely, sharding is a great idea. There are many technical challenges how to implement it. So in particular, cross-shard transactions pose a lot of interesting questions. So I'm looking forward to Alberto addressing these.
Okay, I see. Okay, thank you, Grigory. So, Alberto, are you here right now? Do you hear me? Okay, so let's continue with the talk. Thank you very much, Grigory, and thank you very much.
I actually have one question that maybe.
Okay, sure, you can ask this question without any problems.
It's not clear to me what kind of underlying blockchain technology we are talking about. Is it a proof of work permissioned and non-permissioned blockchain, or it is more like classical Byzantine agreement permissioned blockchain, or your sharding techniques actually oblivious to the actual consensus algorithm running within each shard?
Alberto, this is a question for you.
Yes. I was hearing a bug voice. Yes, so actually they're oblivious. We're not talking about the Sybil resistance mechanism, namely the way to select those nodes. There could be proof of work, there could be proof of stake if you want a more open system, but there could also be a traditional access control in case we have a totally permission system, or we could have anything in between that would work. Does that answer the question? I think I lost you. Can you hear me?
Yes.
Yes.
So my question is, yeah, okay.
Sorry, yeah?
Yeah, there is a lag, I think.
Sorry. Yeah, the short answer is it's oblivious to the Sybil resistance mechanism behind.
No, but with consensus algorithm you use in every shard.
Which consensus algorithm we use in every shard? So this is oblivious to the techniques. We've built our system based on BFT Smart as an academic prototype, and others based on Blockmania. But any inter-shard consensus protocol would actually work. Any BFT-based consensus would work. Hot stuff would do the job.
Can it be like proof of work as well?
Well, proof of work could be used to select the nodes, but Nakamoto consensus cannot be used in order to have inter-shard consensus.
Thank you.
So here is how S-BAC would work. That's one of the ways to achieve it, one of the proposed ways. So we have the transaction, the one as before, and I see here, through time, the actions of the client and of every shard. So first thing that would happen is the clients would broadcast the transaction to the input shards. That's, as S-BAC says, only to the input shard that are concerned about the transaction, namely the input shard that handle either X1 or X2. So you can see here those little boxes called BFT. If you open the black box, they're running a consensus algorithm within themselves. As we mentioned, those could be running hot stuff, could be PBFT, or could be any PBFT-based consensus algorithm there. So I won't open too much those black boxes and just call them black boxes if they run BFT inside of them. So what happens is the shard 1 and shard 2 receive the transaction, sequence it by saying, look, is this transaction valid to me? So does X1 exist on my shard? And shard 2 would say, well, does X2 exist on my shard? Is it valid with respect to its own object, not respect to the other objects? If it is, they would lock them. So this means that subsequent transaction that would come and try to use or spend X1 or X2 would fail. Then, if shard 1 believes that the transaction should go through, again, with respect to its own object, because it has no idea about it, would send a pre-accept to the other message, to the other shard 2. And shard 2 would do the same and send pre-accepts to shard 1. Then the shards would again run BFT consensus, and if they received all pre-accept messages, then they would delete X1 and X2, or inactivate X1 and X2, and create Y1 and Y2 instead. If any of the shards emitted a pre-abort, in which case they would unlock the input object and just abort the transaction. Nothing more would be created. It's important that the transaction stays atomic. Either it's totally executed or it is not. Then, in the case the transaction goes through, they broadcast accept to the client to let him know, and they would send a signal to shard 3 to ask him to create the output objects Y3. And so these could be seen as a two-phase atomic commit, in the sense that the phase 1 would be the vote, and then the commits on the phase 2. Atomix is very similar, so its concurrent works to S-BAC, and it says, well, look, instead of sending pre-accepts and pre-aborts through every client, through every shard, sorry, we would just send it through the client, would channel those messages and reflect them back to shards. This allows to have a linear complexity in the number of shards, assuming signature aggregation on the client. And so how does it achieve linear scalability? Well, look at that graph. It means that while some nodes are busy executing the transaction of the object they're concerned with, so X1 and X2, all other shards could actually be there executing at the same time non-conflicting transactions on object that they manage. And they don't have necessarily to talk with each other, unless as part of the cross-shard consensus protocol. So the two techniques that the one technique, S-BAC and Atomix, that I explain now, end up to be very tricky to build in parallel, to build in practice. And this comes when we take the academic prototypes and try to build real systems out of it. And we realize that there are some fairly tricky concerns there, which make them unsecure under parallel compositions. And here we're going to see why. So there are attacks then, when you implement them naively, that would allow you to double spend any object. So this means that there is an adversary that doesn't even need to collude with any node. So be honest on the system, act as a client, or just be a passive observer and then interact with the system. And it needs to reorder network messages, but not even always. Not even all the attacks require that. So here is an example on how such an attack would work. This is just one of the examples. The goal here is to double spend X1. So well, let's take concrete examples. Let's see how it works. Here we have the transaction as before, transaction T, where X1 has 10 coin, X2 has 5 coins. So we want to double spend the 10 coin. And then Y1, Y2, and Y3 should be created as output. As you see, the transaction T should be valid in the sense that the sum of the input coins are 15, as is the sum of the output coins. So in order to make that attack work, first we will craft a special transaction. The special transaction is T prime. It's exactly as transaction T, but instead of X1, we use a new input object, X1 tilde, that actually does not exist. So this transaction should and will be aborted by the system. And so first we send such a transaction. So we submit T prime to shard 1 and shard 2. And what will happen is, well, shard 2 will observe X2, which is valid, so it will lock it. So blue means locked. And shard 1 would say, well, look, sorry, but X1 tilde does not exist, so for me it's an abort. So transaction T prime will eventually abort. However, what happens is that now there is a race condition where the attacker sends transaction T to the system. So imagine that T prime, its execution is temporarily stopped, where the picture shows, and transaction T is racing and coming in. So what happens? Transaction T hits shard 1. Shard 1 says, well, no problem, X1 is actually valid. So for me, that's a pre-accept. However, shard 2, which says, sorry, for me, it's pre-abort because I already locked that object. This means that there is a concurrent transaction also trying to spend X2, and such transaction came first. So as a result, the transaction will abort. So as you see, the shard 1 emits pre-accept, however, shard 2 emits pre-abort. Shard 1 will realize that at least one shard said abort, shard 2 the same, and so they all will emit abort. So nothing seems happening here. However, the attacker recorded the message pre-accept T sent from shard 1 that it will use later on, and we'll see how in a second. So now the first transaction T prime keeps going. So what happens is that the pre-abort T prime hits shard 2, which says, all right, shard 1 wants to abort, so I unlock X2 and I emit abort, and shard 1 already said abort, so transaction T prime aborted. So now nothing happened on the system. However, the attacker recorded pre-accept T emitted from shard 1. So now, next phase of the attack, what happens? The clients simply send a new transaction to spend X1. So for instance, it would move X1 to a new account that he owns. So X1 does not exist anymore. And the next phase is now sending back transaction T exactly as before. So shard 1 receives transaction T and says pre-abort. Why? Because X1 does not exist. We just spent it on the step before. And shard 2 says, fine, X2 does exist. So I lock it and I emit a pre-accept T message. So now, if everything goes without the attacker's intervention, shard 2 receives pre-abort and the transaction should eventually abort. However, the attacker now races shard 1 by emitting his pre-recorded message from the previous step, pre-accept T, and send it to shard 2. So shard 2 does not wait, so it receives a pre-accept. It thinks that it comes from shard 1. And then what will happen is that shard 1 would say, fine, I said pre-accept. And it seemed to me that shard 1 said also pre-accept. However, it was the attacker who said that. And then shard 2 will create the output objects, Y2, and emits accepts to the client and accepts to shard 3. Shard 1 may not be fooled in the sense that he remembers its own decision, namely pre-abort, and so it does not create Y3. But that's still a problem. What's the output? Before the attack, we had two input objects, X1 and X2. And now we have some more coins. We have Y tilde, the account where we transfer the original X1, and then this hybrid position where we have Y2 that has been created and Y3 which has also been created. So as a result, we have now 24 coins, while before we had 15. And so this is the first lessons that we had. So we tried to implement those as part of ChainSpace at the time, chainspace.io. And we realized that those attacks were exhibiting themselves when stress testing the system with a big load and a lot of transactions there. And then observing that, we were not really understanding what was going on. And looking deeper, we realized that race condition. At the beginning, we thought that this was very easy to fix. At the end of the day, potentially some sequence number would do the job. But eventually we realized that sure, a sequence number would help, but it's not that trivial to fix. And this ended up being another paper published at Euro SMP this year. So the attack I showed you is attacks that focus on the interaction on the first phase of the cross-shard atomic commit protocol. But there are many. I showed you one, but this table shows all the possible attacks. It's not for you just to go through and retry to execute all of those, just this is one of the possible attacks. And they're also possible to have attacks replaying messages of the second phase of the cross-shard atomic commit protocol, which are not discussed here. So what caused this issue? So this was fairly obvious once we identified it. Was, well, input shard cannot associate protocol messages to specific protocol executions. They have no idea that the replayed message came from a previous instance of the protocol. Not at least how S-BAC and Atomix define the protocol. And output shards that are not also input shard, so in that example was shard 3, do not experience the first phase of the two-phase atomic commit protocol, and so are a bit lost because they receive message saying accepts and they can only believe it. And so we thought it was an easy fix. So at the beginning we said, oh, okay, fine, let's add sequence number, right, to prevent replace attack. But that ended up to be not that easy, in the sense that if we had global sequence number across all shards, we would destroy the linear scalability of those systems. And then what if we would wait a little longer just to make sure that we receive potentially multiple messages? And if we receive multiple messages, we may detect that one of those would be replayed, and so know that something was wrong. But this first is not trivial to achieve without relying on synchrony on the network for safety. And also that would prevent us from running at network speed, which would degrade the throughput. So here is the final solution that we came up with. So this is work with my co-authors that you can see here. And the system is called Biscuit. So first fix, we add sequence number. This is fairly expected. However, the way we need to add those sequence number is we don't add them per shard globally, but we need to add them per object. So now every time we create an object, we also create a sequence number associated to the shard. To the object, sorry. And then each shard, for instance, shard 3 in that case, would create a series of finite amounts of dummy objects that also come with a sequence number that they would use in whichever transaction use them as output objects, but does not require the shard to be an input object as well. We'll see how that works in a moment. So here is the Biscuit protocol. First, the client submits a transaction, as before, but with two differences. First, it proposes a sequence number, which is bigger than the sequence number associated with every input object. And also, since the client with the transaction T wishes to consume only object X1 and X2, but create an object on shard 3, Y3, it needs to add a dummy object of shard 3. So it would simply reference one of the object of shard 3 and says, we pretend that this is an object that needs to be consumed. This is a trick that forces shard 3 to be part of the first phase of the protocol. So now, shard received the transaction. What's the first thing that happened? So first, check 1. As usual, they will check that the transaction is well formed and that all input objects are active and that they can be used for the transaction. Then check 2, every shard would make sure that the proposed sequence number is bigger than the sequence number of all the objects it manages. If the check failed, before we were simply unlocking objects and emitting abort, now what we do is that we increment the sequence number of every object of the shard by st plus 1. Otherwise, we lock the object, store the tuple stt, so the sequence number and the transaction, so we lock the transaction for a specific sequence number, and these will act as a session identifier for the protocol. Then we emit pre-accept, and here we use a hybrid approach from Atomix, which we're canalizing the message through the clients, and S-BAC, which we're simply broadcasting the message to all the other shards. What we do here is that we send the pre-accept messages to a specific party called the transaction manager, and I'll tell you more about it in a second. That special party aggregates the messages. If they're all pre-accepts, it emits accepts to all the shards. And then the shards, if they had a memory, in their cache memory, the tuple t and st, they can inactivate the input objects, x1, x2, and the dummy object d3, and they would create y1, y2, and y3, and shard3 will update and create a new dummy object so that it never runs out of those. So the issue 1 is fixed as follows. So before, the problem was that input shard could not associate protocol messages with specific protocol execution. So now sequence number would act as a session ID effectively that would solve that problem. And issue 2, output shards that are not input shards that first did not experience the first phase of the protocol. Now we use a trick of dummy objects to make them experience the first phase of the protocol as well. So now, what about the TM? Well, the TM can be anyone, actually. So it turns out that to aggregate the pre-accept messages, you do not need to know any secret. So anyone could be it. And by anyone, I mean literally anyone. It could be a shard. So we could ping every node of a separate shard until we reach an honest node that wants to aggregate those messages for us. Or it could be a single party. Again, if that single party fails, it's not the end of the world, because anyone could just observe that there was an incomplete execution and read from the input shard the pre-accept messages and complete it by aggregating them and completing the second phase of the protocol by sending accept messages. So we implemented this as a Java fork of ChainSpace based on BFT Smart. So BFT Smart was to run the consensus within the shards. And so this is a prototype, as it's based on BFT Smart. We cannot have high performance, but what we want to demonstrate here is that we still achieve linear scalability despite the countermeasures. So here's the graph. As you see, it goes up fairly linearly, and it's the example of execution with 2 input objects and 5 input objects. There is one line, blue line, that says, what if we didn't have replaces? What would happen? So the case where we're vulnerable to replay attacks, and the performance hits that we take in order to add the dummy objects and the sequence numbers. And here is, for the client's perceived latency, how it increases when the transaction loads increases in the system. But as you can see, it's still fairly low, still under 1 second for a load of 1,000 transactions per second. So that's the conclusion of the first part. So the conclusion was Biscuit. How does it work? It's a mix about S-BAC and Atomix by using the TM instead of the client to canalize all the protocol messages. And we achieve high throughputs in the sense that we have linear scalability. The throughput increases with the number of shards that we add in the system. BFT resilience, and we have a fairly fast finality as well. So that's the conclusion for the first part. Now I can go on the second part, which is shorter. Would you like to have any questions now about the first part?
So I don't see any questions in the chat.
Well, that's not a problem. We can continue.
I can ask a question.
Sure.
Okay, so one question is what kind of concurrency control you use within each shard, and if you have to determine your vote, if it should be pre-abort or pre-commit.
So
is it pessimistic?
So it's fairly pessimistic, yes, because what we do is that once we observe so object can be used only once, right? So it's like UTXO and like coins. Once we receive a transaction that attempts to spend one, we lock it, which means that subsequent transaction that try to use that object will automatically fail. And then only if the transaction is eventually aborted during the second phase, we unlock the object that can later be used. That's not optimistic in the sense that imagine that we had a transaction that was being aborted. Potentially legitimate transaction that came after would have been rejected just because the first bad transaction is not completed yet.
Mm-hmm. Okay. How do you deal with the coordinator failures, and in particular Byzantine coordinator who could lie, say something that is not lie about votes, lie about basically anything?
So by coordinator, you mean the TM, the transaction manager?
Yes, so it was not completely clear to me. So you said, I think in the beginning, you said that client is the coordinator, but then you added TM into the picture.
Right.
So, but in 2PC, you need to have a coordinator, right?
Yes, exactly. So in Biscuits, there is a special party called TM, which is the coordinator. In Atomix, so another protocol, the client is the coordinator. So in Biscuit, first, in Atomix, how it works is that the other said, well, look, the clients that acts as coordinators has all incentives to keep the protocol alive because it's spending its own coins. Otherwise, its own transaction would be blocked. So, of course, it could be bad, but that's how the protocol goes. In Biscuit, we're slightly different. So first thing to note is that the coordinator cannot really lie. The only thing that it can do is to aggregate the messages and send them or not do it. That's the only two things that it can do. It can also send partial messages, bad messages, but that's the same thing as just not sending them. There is no signature.
Yeah, so this is a bit suspicious to me that you said that there is no signature. So how anyone can are there any certificates associated with these messages that that would prove that the coordinator is actually doing something which is legitimate, which was supported by the actual shards?
So the coordinator does not sign. Every shard signs its message.
Oh, okay. So the shards do sign. Okay, that
Yes,
was something I
yeah, no,
missed.
that's sorry, that I forgot to mention, but that's very important. Every shard signs its own message. Any message that it sends, the coordinator aggregates them. Either it packs all of them into one big message, or if we use a threshold signature scheme, then we can simply compress all the signatures.
Okay, so it can be either multi-sig or threshold sig from every shard.
Exactly.
Okay.
Yes. So if we want to be linear in the number of shards, we need to use a threshold sig, which comes at different expenses, of course. And so what if the TM is bad? Well, the way we implemented it is by saying the TM is actually a shard. So what we would do is we would select a random node in, let's say, a random shard, and let's hope it's honest. So we may send a transaction to that node, see if it does the job, and if it does, aggregates and reflect back the messages. If not, we may pick another one. Eventually, after we picked f+1, we will know that the honest shard will do the job. This is one way of doing it. Another way is to say, look, we straightly send it to f+1, a node of a random shard. And we know that at least one of them will be happy to aggregate and send. And another approach, more optimistic, is to say, well, look, we have a separate system that simply reads all the results of the first phase of the protocol on the shards, on the logs shards, and just make the protocol progress for every shard. Since we only require that separate system for liveness, it's literally necessary to have one honest party in the whole system that is happy to do it for the system to work.
Okay, yeah. So I'll let you make progress. I have more questions, but I think in the interest of progress, we need to just continue, carry on. Yeah, thanks.
Absolutely. So we are now at phase part 2. So reducing latency. So this is a different story. We say, well, now we have a system. Let's try to use a side infrastructure in order to reduce latency there. So this is what we have from part 1. We have a sharded system that has linear scalability, high throughputs, BFT resilience, and fairly fast finality as well. However, if you look at how S-BAC at least works, you have the client that sends messages, BFT happens within shards, they need to communicate with each other either through a broadcast or through ATM. Another BFT round needs to happen, and then the client needs to be notified. So the total latency would anyway be the slowest shard of phase 1, the slowest shard of phase 2, and the time for all communication to happen. So we cannot reduce latency more than a certain threshold, knowing that we need to do all of that. So here is the ambition of what we would like to add next, is we would like to bring those payment technologies and make them practical for retail payments at physical points of sale. So it means that we could go and buy coffee and the transaction needs to be confirmed fast enough. So what we want is low latency, that's new, but we also want BFT resilience, fast finality, and high capacity. So high capacity here, what I mean is that we need to be capable of handling a very high load on the system without crashing it. So the current state of the art or current industry, let's say, the system is fairly disappointed. So first, retail payment systems are centralized, usually built up to mainframes and have manual switch or a weekly automatic switch to have a master-slave architecture. Slow finality, so if we look at the European Target 2, for instance, it takes minutes, and anyway, the capacity is so slow, so those systems can handle so few transactions without crashing, that it ends up that banks don't simply send the transaction through those systems, but what they do instead is that they send a net aggregate payment at the end of every day. So they incur a gigantic credit risk for all payments they weekly finalized on the moment at the retail point of sale. So we can see that they're just centralized at the end, low finality, very little capacity, and low latency. So let's try to see if we can replace such payment networks with more modern solutions. So the idea here, I'm going to present you a system called FastPay. It's presented as a fault-tolerant settlement systems, but I'll show you how to integrate it into this discussion that we just had. So this is work with my co-authors that you see there, and the work was done at Facebook Novi. So here is an overview. So we had the primary system. Here in white, we can say a sharded system, but at the end of the day, this FastPay system could be hooked up as a side infrastructure to anything. Could be a centralized system, could be a non-sharded blockchain, or could be the sharded blockchain we just talked about before. We like to hook them to this kind of system because then the sharded blockchains give you linear scalability and high throughput, while FastPay is just there on the side in order to bring latency down. And we can have multiple different FastPay systems, so independent from each other, that would be hooked to the same primary system. So FastPay is very different in nature from blockchains. So where traditional BFT-based blockchain would run Byzantine consensus within each other in order to sequence the transaction, FastPay is uniquely based on consistent broadcast, which is a much weaker primitive, but that makes it much easier to implement and much more efficient. That we'll see later. We implemented a system which is fairly close to a production-ready system, and we achieve very good performance after that. So how does it work? So the system is extremely simple. So we have a sender, we have a recipient, and we have a set of nodes. So that's the side infrastructure. It's a committee of nodes, a BFT committee. We need more than 2/3 honest, but we can tolerate some that are bad. So the sender has accounts on that side infrastructure, that I'll come to that later, and initiate a transfer order. So basically it sends a message to every member of the committee and says, I would like to transfer 5 coins from me to the recipients. Every node separately verifies the transaction. So it verifies that there are enough funds, verifies that some sequence numbers are okay. Here are traditional sequence number per account. And if everything is fine, they would sign the message, so basically countersign the message, and send them back to the sender. So every node would do that, every honest node at least. And then step 4, 5, or 6 are all equivalent. What the sender does is that it aggregates the signature from the nodes, and now it effectively has a promise that the payment will eventually be executed. So this is called a confirmation order. And now the sender can do multiple things. Either it broadcasts the confirmation order back to all nodes, or it can simply show that confirmation order to the recipient, and the recipient will be convinced that now it can take that confirmation order, broadcast it to the nodes, and the payment will be finalized. There is nothing possible now in order to reverse such a payment. It can either be completed or hang there until anyone, the sender, the recipient, or anyone else, decides to broadcast that confirmation order. So that's specifically useful. So step 5 is specifically useful when you try to buy a good at a shop, where you simply need to show the confirmation order to your merchant, which then can give you the good, and at any point later, broadcast the message to the nodes. The last step, the nodes verifies that the confirmation order is signed by enough nodes, so 12 plus 1 nodes, and just updates the balance of the sender and the recipient, and update the sequence number that comes with transactions as well. So this is a very simple system, and it turns out that it can be easily we can easily scale it horizontally. So the way we would do is, instead of having every node composed of a single machine, so every node, so every trust authority, can now have multiple backends and separate that client's accounts across those multiple backends. So that's not very complicated to do, but I won't talk about right now in the interest of time. What will basically happen is that the client would send the first message, so step 1, the transfer order, to a special machine that would just observe the balance, send back the message, and then upon finalizing the step, the messages need to hit the right backend, which can be either sent internally by the system or directly by the client. So more of that would be on the full paper. So now, how do we fund such side infrastructure, and how do we hook it to a primary system? So here we take the example where we have a smart contract running on a primary system, but this could also be a database driver in case we have a centralized system or a more traditional alternative. So the smart contract needs to hold a few things. So it needs to hold the committee information. It needs to know who the side infrastructure are, so their key, their address, and their name. It needs to have the total funds in the contract, so the smart contract can handle funds. And the last transaction index, that will come to that later. And the redeem log, which will also come to that back later. So how does it work? Now, the sender at the beginning has no account and no money on that side infrastructure. It's a new side infrastructure. However, it has money on the primary infrastructure. So what does it do? It sends a traditional blockchain transaction and hitting the smart contract that says, please transfer some of my funds into the smart contracts. That is step 1. Step 2, we call it a synchronization order, because every committee member, so every node of the side infrastructure, has a blockchain client, it realizes that some funds have been transmitted into the smart contracts and then creates the equivalent number of coins into the side infrastructure database. And yeah, they would verify the smart contract state and do the updates. That's step 3. So now, to interface it with the primary infrastructure, again, the smart contract also needs a redeem log. So the redeem logs is for the other operation. So to send money from the previous infrastructure to FastPay. So this is the first step here, right? As I mentioned, we send a transfer order, we verify, and now we need to send back a signed transfer order to the sender. This is similarly to when we want to transfer funds to a recipient. But now we send back the transfer order to the nodes, which will update the states. This will also create a redeem transaction, so the sender now can take the confirmation order, which has a special recipient, which was the smart contract, and send the transaction through the blockchain, through the primary blockchain. The smart contract would verify the redeem transaction, and that's where the redeem log comes into account. So to prevent the sender from double spending the transaction, the smart contract needs to have a growing state in the number of clients, on the number of accounts that it has, where it stores the last transaction index for every client. So upon seeing a new redeem transaction, so not a replayed one, it can simply update the states by sending back money from the smart contracts to the specified primary accounts. So it's pretty much the same thing as before, but instead of sending money to a new recipient, we send money to a specific smart contract, we then send money from the blockchain to the blockchain account. So we implemented that system in Rust using networking, and we use Dalek as cryptographic library. So for the throughput evaluation, we used one AWS machine with multiple processes to emulate multiple backends from the same authority. And we try to see what's the maximum load that such a machine can take, the maximum number of transactions per second that we can have processed. And so here is how it goes. And you can see the numbers are fairly high. So we managed to achieve something about 150,000 transactions per second by having 50,000 concurrent transactions. So concurrent and independent transaction in this case. We show that the more processes we add to the machine, the more transactions per second we can process, and then we plateau out. And that's because our physical machine has actually about 46 or 48 physical cores. So this is simply because since we implemented everything into a single piece of hardware, we run out of physical resources. And that second graph is fairly similar, but it shows how the throughput is influenced when the transaction load increases. And we can see that we can throw 1.5 million transactions at the same time into the system, and the system would not crash and still do not degrade performance. So here is the throughputs and its degradation with the committee size. So of course, if you increase the size of the committee, of the FastPay committee, you will have more signature to carry on and potentially more people to contact. And so verifying signature takes time, and that's why we see that degradation. However, we can still have about 880,000 transactions per second with 20 authorities, which is a fairly high number. For the latency, we measured using the following setup. So we put one client in California, that's the blue dots on the left, and one client in London, and we set the committee in Stockholm, just to measure the latency from a client which is very close to the committee and one that is very far away. And here is how it goes. So that's the confirmation order time, the time that it takes for the transaction to be finalized, settled. We see that the UK client basically takes one round trip and is not influenced by the committee size. And that's simply because since the client fires all the messages at the same time to all authorities, it simply waits for any 12+1 to receive it, and then we're good to go. And for the further clients, so the US-based client, we see that we go to 200 milliseconds, something like that, and that's because of network delay mainly. So the worst case efficiency, so we also test that. So we tested what happens if now we try to crash some nodes on the fast-paced systems. And here we realize something that may be obvious. It is that since we have no leader, because there is no consensus going on, actually nothing changes. The performance is not degraded at all. Of course, if you kill too many nodes, more than 12+1, then you lose liveness, the system does not work anymore. But on blockchain systems, depending on how they're implemented, if you have a bad leader, most of them will slow down. And so this is one of the big implementation lessons that we learned out of it, is that simplicity really favors robustness and performance. If you have simpler system, even though you may think that they have higher theoretical complexity, if they're simple enough, it's usually much easier to implement them in a much more performance-driven way. And the second one is that making fast-paced simple in the implementation was hard. So as you can see, the protocol is not very complicated. It's simply consistent broadcast, but implementing it was fairly hard, implementing it right. So it took us 2.5 months and 3 engineers in order to reduce the number of lines of codes to less than 4,000. And just to show you the work that it took, it was more than 1,500 Git commits to have the code up and running. And so we tested everything on AWS. I give you there the name of the instance that we use in case you want to reproduce and test performance for yourself. And it's nice to note that those machine costs about $5 per hour, and that you can potentially run all the retail payment system in the world with machines that are $5 per hour per authority. And so that's the conclusion of part 2. FastPay foregoes consensus using consistent broadcast. It has a simple design, low latency, high capacity, and it is very robust. So this is the conclusion, the general conclusion of the 2 parts. So part 1 was about increasing throughput using sharding. And the second part was about reducing latency using a side infrastructure. That was the fast-paced system. And so remember, this is how we could put them all together. We may say we use as a primary system the whites, part 1. We could use a biscuit, the one we discussed before, and then hook several independent fast-pay to the primary system. So remember, the main conclusion from the cross-shard consensus is that it's tricky to implement right. It's very easy to get it wrong. And building a BFT side infrastructure from consistent broadcast is actually very simple. It works, and it's fairly robust and easy to scale. And that's it. So for the first part, I hope you got the main concept of sharded, and you also see why they're tricky to implement. And from the second, a simple technique to make blockchain payments so low latency through the use of side infrastructure to make them even usable at physical point of sale. So really in real life. And then how you can hook everything together by having an interface. Smart contract, the first structure of the second part. And that's it. That's all the presentation. I'm happy to take any questions if there are any.
Thank you, Alberto. I don't any questions being asked in the chat.
That's good. That means everything is clear.
Right. So I guess we have something like what 10 minutes for questions now.
Yeah, we can wait some to see if any question come up. Otherwise, it's perfectly okay.
I can ask you a quick question.
Sure.
While we are waiting for maybe other people asking questions. So you mentioned that for the side infrastructure you use atomic consistent broadcast. So it is by consistent broadcast you mean Braha type of broadcast?
No, we don't use reliable broadcasts. It's a signed echo broadcast from Cachan's book.
It is Braha broadcast. Okay, yeah, Braha. This is
Okay.
I know. Yes, that's an eco broadcast is the other name for it. So my question is, I actually in your talk it was not so much clear to me at which point exactly you use it. You just said that you use it, but I did not see in the protocol when this happens. And
Right.
related question is that Braha, eco broadcast actually can't tolerate the failure of a sender, right? So you need to do something if because obviously it's not as strong as consensus.
Yeah.
So yeah, if you can maybe clarify these points.
So there are two very good questions. Let me come back to the slide. So first, where do we use it? So here is how the instance would work. We have the sender that sends the first message, that is the transfer order, the verifications, so let's forget it, and step 3, that's the echo, the signature from every node back to the sender. Then there is the aggregation step, and step 4, let's say, is when you ready back the message to complete the signed echo broadcast. It's actually that every client, so every sender, use an instance of consistent broadcast with those authorities. And those can happen in parallel. Every client initiates such a consistent broadcast with them. That's where it happened. About failing senders. Yeah.
Yeah, so the broadcast happens within these green boxes, right? This is where the actual broadcast occurs.
Every green, yeah, is a replica.
Okay. Okay, fine. Right. So okay.
It's
and if sender fails,
if sender fails, it's very important that I should have noted it. So every sender can only fail, if it fails, can only do a harm to its own account. So every accounts are pre-funded with sender's money. And that can happen if that a sender may fail and end up in an inconsistent state so that its own account is unusable. But since it initiates the consistent broadcasts himself with the authorities for only its own accounts, it cannot interfere with accounts of other senders. But it's perfectly true that a dishonest sender may end up doing harm to himself.
I see. So it's basically in fact account is a kind of shared object with a single writer. This is what happens.
Yes.
You might be interested to look at the work of Petr Kuznetsov and other people. It was published in POTSI, I think. POTSI and this covered the past 2 years, something like this.
Yes.
And Rashid Girawi as well. So they actually model Bitcoin as a collection of shared objects with a single writer. And they argue that, in fact, you can do the Bitcoin without consensus for that reason.
Yes, I think I saw that actually.
Yeah. So I think what you are proposing here is because the payments have this kind of a weaker semantics. You can like every account has a single owner. You can do tricks like that, so you don't really need consensus.
Absolutely, that only works because payments are commutative. Yeah, it doesn't matter the order on which you receive your payments in, since it's just a sum. Yeah. But it matters the order in which you take your money out. That's why we need sequence numbers there for the consistent broadcast.
Right. Yes. Okay. Right. Yes, it's very interesting. Thanks. It's a very good talk, and yeah.
Well,
I'm actually gonna read the papers. It's yeah. So so what are the open questions? Or you?
Oh yeah.
We already solved everything.
No. There are many. I didn't include in the talk because it was perhaps too much time. So the first that we have is that those side infrastructure as FastPay cannot really work on their own, in the sense that what if you need to change the validator sets? What if you need to expand it or decreasing it? In that case, you really need the full power of consensus. So the way we kind of take that problem out is by saying, well, look, we do have consensus, just not in the FastPay system. We have it in the primary infrastructure. So when you need consensus, well, you simply use the smart contract semantic there. But it's not entirely clear how to make it safe. So we didn't push the work there. It's perhaps easy or perhaps it's tricky. We don't know yet. Second very big open questions is more related to see there. So we see that we have some threshold signatures. We see that we have some distributed identities. Can we use some threshold issuance credentials in order to have some blinded accounts that don't leak the full value of every account in FastPay? So intuitively, yes, but I wouldn't know how to do it straight away. So this could be an option. I think those are the two main questions. The reason why we keep presenting it as a side infrastructure rather than a payment system on its own.
Okay, so you have problems with anonymity. This is what you're saying. Yeah, I mean the second question.
That's exact. That's the second. And the first is that how do we change the validator, the authorities?
Yeah. So the first one is more like a classical distributed computing question. So this is reconfiguration, right?
Yeah.
So you can presumably use something like FastPaxos because you have this full-blown, not FastPaxos, sorry, vertical Paxos, a Byzantine version of vertical Paxos, since you have this like a blockchain, normal blockchain infrastructure on the side. So that could be used to store configurations, and then you just need to synchronize the infrastructure with that. Yeah, so that's an interesting. Yeah, that's yeah. If you're already working on it, I don't know if you're already working. It's something I would personally be interested to.
Oh, absolutely. Let me know. So I'm not working on it, but I would be happy. Let's keep in touch. I mean, the naive solution there, but it's naive, right? Is we have a graceful shutdown. So we empty out every account from the FastPay infrastructure back to the smart contracts. We give back the funds to the owner, and then we start over. We start over with a new. I mean, that's naive, right? And it's very inefficient. I mean, it's a lot of stuff. But it shows that there is at least one solution. Now let's try to find something that works better.
Very well. Yeah. Thanks.
Yeah. Well, thank you very much for the questions.
Can I ask a little bit of questions also? We have like two minutes more, so I have a question whether, did you try to, so you have this biscuit and fast pay parts, right? Did you have some graphs or plots where about their performance together? Like probably you have like, because like somebody could understand, okay, you have low latency for biscuit, but why you have low latency or vice versa, high throughput for biscuit, but low throughput for fast pay? Like, have you tried to merge them together to get some numbers?
So you don't. It doesn't really make sense to merge them together in the sense that first you have the primary system that needs to pre-fund accounts on FastPay.
Yes.
So you need, once it's pre-funded, you can use them as much as you want within each FastPay system itself. So it's not like you need to do one every time you want to do the other. This happens only once. Also, high throughputs. I have to say, Biscuit is fairly high throughput. I mean, I don't know how you define it, but over 100,000 transactions per second. Note that is more than what Visa and MasterCard combined do. So it's a fairly high amount of throughput as well. It won't go faster than that. That's the point. So if you need more capacity for FastPay, you won't be able to do more than that. So that's why the linear scalability on Biscuit may help. But then what you would do, you would use several independent FastPay systems to each other. Now, this brings me to another consideration, is if you have multiple independent FastPay systems, you cannot pay people from one FastPay system to the other. They're absolutely separate. Could be a nice research question to know if it could be a cheaper way to allow such transactions, and would it be faster than going back to the main chain? I don't know that.
Okay, I see. That's kind of interesting. Thank you for very interesting talk, Alberto, and thank you, Grigori, for a lot of questions. I hope someone will join the Zoom meeting that we will have, like below my finger. There is a link to Zoom meeting. So, good luck, guys, with the Zoom. But I guess there are not so many questions left. So the talk was perfect in this sense. So thank you, Alberto, again.
Thank you.
Okay, bye.